This is FRM Part 1, Book 2, Quantitative Analysis, and the chapter on linear regression. With a linear regression model, we have two variables. And what we believe is that there is some kind of a relationship, whether it's positive or negative, between these two variables. And of course, that must mean that there's some good level of correlation coefficient between the two variables. But the relationship here in linear regression models is a little bit different. What we do is that we separate the two variables. One of the variables we call a dependent variable. The other variable we call an independent variable. And we use the independent variable to explain the dependent variable. Quick example, let's take the number of hours that my children spend on one of their German tests versus their scores on their German test. I mean, it makes sense. It makes sense that what we're trying to do is explain their performance on the exam, so we do it by analyzing the number of hours that they each study. It doesn't make any sense to do it in the opposite direction. So let's look at the learning objectives here. Note that the command or action words are lots of explain and describe and define and summarize and interpret. Interpret's an important one. These don't necessarily sound like calculate or compute, but you ought to be ready to be able to do some kind of minor calculations, and we'll go through these in the slides. Here's the good first question. What is regression analysis? Measures how changes in one variable, called the dependent or explained variable, how those changes can be explained by changes in one or more other variables. Now, in this chapter, we're just using one. This is called a simple linear regression. Later on, we'll do multiple regression. So here's a quick example. We could take some independent variables like interest rates and inflation and maybe oil prices and consumer sentiment and all that kind of good macroeconomic variables. What we do is establish the link by forming this regression equation to try to explain the dependent variable. And that dependent variable in this case is going to be GDP, so the size of the economy. It makes perfect sense that if the economy is going like this, then those independent variables are probably doing something, right? If the economy is going like this, then those independent variables are probably doing something else. So in this case, simple linear regression, we just have one independent variable. We're going to say something like, during periods of rising interest rates, this is going to have a specific effect on the size of the economy as measured by GDP. Now let's look at the relationship between two variables here. Let's call this a scatter plot. So all we're doing is collecting data on a y variable and an x variable, and we're plotting them on a graph. All right, so in this case, let's suppose that the return earned by a hedge fund, which is the dependent variable, may depend on the length of the lockup period, which is the independent variable. So we've got that return going up the vertical axis, and we've got the length of time going on the horizontal axis. And just by looking at this, what is that? 2, 4, 6, 8, 10, what is that? 10 or 12 observation points. That's not a ton. We might need 100 or 1,000 to be able to make this work. What are we kind of looking at here? If you eliminate those two at the bottom right, and you can't do that, of course, that's called data mining. But if you eliminate those two on the bottom right, you kind of see like an upward slope there. It's probably going to be upward slope even with those two variables down there. But what the scatter plot does is it gives you a visual. You can look at this thing and you can say, okay, it appears as the x variable goes up, so does the y variable. And remember, we've got to do this on averages. Just like we spent so much time in that last chapter talking about the mean and the standard deviation. Those are going to be important in regression analysis too. All right, so here's the simple linear regression model. So there's the dependent variable, y hat, over on the left-hand side of the equal sign. And the hat just means that these are samples, not population. And then there's the independent variable over on the x. That's the explanatory variable. And then we have some parameters of the regression model. The first one, that beta hat sub 0, that's always the y-intercept. So that's the intersecting point up on that vertical axis. So that's where we start. And that can be positive or negative. Doesn't have to be either one. Just really depends on the relationship between x and y. And then beta hat 1 is the measure of the sensitivity of changes in y to changes in x. And that's the slope of the regression equation. And that's probably really important to remember, that beta 1 hat is the slope of the regression model. And comma, by the way, that beta there is the beta that you read about in equity securities. And then all the way at the end, there's an error term. My econometrics professor always gave a really, really cool explanation for what that error term is. And of course, the expected value of the error term is 0. You don't ever expect to make an error, but you know that you're going to make an error. And he would say to us, look, you guys can study for 100 hours for one of my tests, but you're not going to make a perfect score on my test, because nobody makes a perfect score on any of my exams. And that error term captures how far away you are from perfection. So I always got the good sense from my econometrics professor that that error term is really important. All right, let's go ahead and put this model into the graph. So there's the y going up the top. There's the x going horizontally. There's the intercept term. Notice that it is a line, right? Simple linear. Line is part of that word linear. So this is an upward sloping. So beta 1 is going to be positive. In this case, the intercept is positive. So there's beta 0 on the left-hand side going up the y-axis. And then there's the linear relationship. And so the slope of the line measures the change in x and the change in y. Beta 0 and beta 1 are known as the regression coefficients. One is the intercept, one is the slope coefficient. Here, getting back to the error term, it represents the portion of the dependent variable that cannot be explained by the independent variable. In other words, it represents effects from the independent variables that are not included in the model. At some point, we'll talk about model misspecification, and it's clear that this is a linear regression, whether it's simple or multiple regression, and you can't really have thousands of variables over there on the right-hand side of the equal sign. So remember, this is not a perfect model, but it's a pretty good model. And so let's swing back to that first example. So here's here in my circle point. So GDP growth is equal to an intercept term plus slope and times the x variable, which is interest rates there. All right, and so that E term, that error term, it represents the portion of GDP growth that can be explained by variables other than interest rates, like stuff that I talked about earlier, inflation or oil prices, or whether there's a Democrat or a Republican Congress or president, foreign exchange rates, all sorts of other macroeconomic variables can be thrown in there. All right, let's go ahead and talk about some formulas for the slope and the intercept term. Now, the beta 1 hat, this is by definition. And I bet you remember this from, old-time investment stuff and even some capital asset pricing model material that we covered earlier. And so beta is always a covariance divided by variance. So it's going to be the covariance between the two variables, right? And remember, that covariance can be positive or negative. I showed you how to calculate covariance back in, I think it was just the previous chapter, and then that's going to be divided by the variance of the independent variable. And then you kind of back in to the intercept term. You take that measure of the slope, beta 1 hat, and you throw it into the rearranged version of the equation in which the expected value of the error term is 0. And instead of using all of the x and y variables, you use their means. So beta 0 is equal to the mean of y minus the mean of x, weighted by the slope. And I bet that makes perfect sense to lots of you. Here's some good assumptions of the ordinary least squares model. Expected value of the error term is 0. We talked about that. The observations are independent and identically distributed. In the economics terminology, that's called IID. And what that essentially means is that you have think of a big old matrix. You have a constant variance term going down here, and the covariance terms are all 0. Another assumption is that there are no large outliers in the data. I mean, that would occur back in my son's example for studying for their German tests. Like if they studied for 1,000 hours for one German test and made a 5% on it, that would probably be an outlier. Of course, as you know, 14-year-old boys, their brains are not fully developed until they're about 25. So who knows what could explain why they do poorly on their German tests. All right, other assumptions, the error term is normally distributed. So go back up to that first one. So the expected value of the error term is 0, but we know that we're going to make mistakes, right? We know that we're going to make errors, and so the error term is normally distributed, which means, and I'm always used to tilting my head sideways because my professor used to draw that error term normal distribution on the board sideways. And so if you think of it that way, I won't do it to you. Hopefully you guys won't get vertigo. But if you think about it, so that means that all of the error terms are clustered right around the middle. And as you go farther and farther away from the mean, which is 0, you get fewer and fewer observations. Of course, linear relationship exists between the independent and the dependent variable. Independent variables uncorrelated with the error terms. We can talk about serial correlation some other day. And the model does not suffer from misspecification, which includes this no omitted variables. So here's an example. So let's do, what are we doing here? Student-teacher ratio. This is really important in colleges, by the way, and average grade. So let's just look at the data in the box just quickly. So if the ratio is 45, the average grade is 76. If it's 43, it's 77. If it's 40, it's 78. If it's 38, it's 78, and so on and so on. So look, if you go down to like 20, maybe the average grade would be 82 or something like that. So clearly, what does this mean? That the fewer number of students in a class, the better is the performance of the class. All right, and so look at the first bullet point. I say something like, let's suppose we do this 500 different times. And then let's suppose that we get out our little Excel. Excel's pretty nifty, and there are lots of other programs that do regression analysis. But in Excel, it's pretty nifty. And so you just put the data in, go to data and regression, and you'll get, let's suppose we get an intercept term of 90 and a slope coefficient of minus 0.3. So there's the OLS regression line. Test score is equal to 90 minus 0.3 times the student-teacher ratio. And of course, we're not surprised that there's a minus sign in front of that 0.3 because it's a downward slope, and there's the picture there on the bottom right. How about benefits of using OLS estimators? All right, OLS can be said to be the common communication medium as far as regression analysis is concerned. There's lots and lots of ways to run regression analysis, but the ordinary least squares is a part of all these statistical packages, so it's really easy to use. But here's more important, is that these OLS estimators are unbiased and they are consistent, which implies that they are efficient. Remember, we're not asking them to be perfect. My econometrics professor never said, hey, this is a perfect model, it's going to work every time. I mean, rarely do we see this in our daily lives. There are mistakes all the time. Those of you who are football fans will know that back in the NFL playoffs, there was a giant pass interference call that was missed that cost a team a trip to the Super Bowl. Just the other day in the NCAA tournament, there was a double dribble that wasn't called that may have cost the team a chance to compete for the national championship. So we're not looking to be perfect, we're looking to be efficient. And efficient means unbiased and consistent. And talking to basketball and football coaches all over the place, they all will say, all we want is the refs to be consistent. If it's a foul here, then it's a foul over there. If it's not a foul here, it's not a foul over there. I have no idea if basketball and football relate to OLS estimators, but I think it's still a good analogy. All right, so this is what we do here. We have this fundamental economic relationship between two variables. So we formulate a regression model. There's the y and the x, and the unknown parameters are beta 0 and beta 1. Then we go out and collect the sample data. We get all of the x's and we get all of the y's. I think in the previous chapter, we were looking at an example that included interest rates as our x variable and changes in GDP as our y variable. And we get together and we decide, are we going to use Excel, or are we going to use SPSS or Minitab or some kind of a software program to estimate the regression equation, and then that regression output will give us beta hat 0 and beta hat 1. That's the intercept and the slope coefficient. And by the way, when I was in graduate school, I always thought it was really silly when my econometrics professor used to say the words beta hat. It just didn't sound very graduate school kind of language with a hat. But clearly you can see on top of it, it's a hat. I don't know what else you could call it. And then finally, we're going to use those estimated parameters to provide us estimates of the true parts of the model. All right, so here's the question then. We can go back. So let me go back here to that formula. Look at the what is that, a blue egg on the bottom right? There's our regression equation, and we then can have the regression output. And what we want to do is we want to say, okay, does the slope coefficient mean anything to us? I mean, in other words, if we were trying to predict the performance of my sons on their German tests, and we're using the number of times that I shoveled snow during this past winter, we can run that. I can collect data and run a regression equation and estimate a set of linear parameters, and I can get some number for beta 1, but it doesn't really have any meaning. So we need to ask ourselves the question, is it economically significant, which in my example with the tests and the snow shoveling, of course that's not. But if I'm going to do interest rates and changes in GDP, I'm going to get an estimate for beta 1. I need to know if it's statistically significant. Now, what we say that is that if that slope coefficient is equal to 0, then it's insignificant. And that should make perfect sense because, let's think about it. If the slope is 0, that must mean that X, like interest rates or snow shoveling, has no impact on my children's German grades or changes in GDP. If it's not equal to 0, then we say that it's significant. But we need to determine statistical significance, and that can only be the result of some statistical test that we can conduct around that slope coefficient. All right, 3 ways to do this. We're going to use critical values, we're going to use p-values, and we're going to use confidence intervals. All right, let's go ahead and state the null hypothesis. All right, so what you do is you create the null hypothesis as if you want the test to fail the null hypothesis. So with interest rates and with changes in GDP, our null hypothesis is that interest rates have no impact on GDP. Notice to the right of the top blue box, X does not affect Y. The alternative hypothesis is the rationale for the economics and the fundamentals of the creation of our original model, which says that, okay, beta 1 is not equal to 0, might be greater than, might be less than. Remember, that slope coefficient could be positive or negative. And what we conclude is that X then will affect Y. Now, if we go back and run this test on my children's grades and snow shoveling, we're pretty sure that pretty certain that we're going to say, you know what, the null hypothesis is correct. Snow shoveling has nothing to do with test performance. But with inflation and GDP, we need to compute the test statistic. And that's what we do in step 2 there. So note we have beta hat sub 1, and then we subtract in the numerator the value of the null hypothesis, which is going to be 0, and then we divide by the standard error. Remember, we're always dividing by some measure of variability to standardize this stuff. Then what we're going to do is get our tables out. We love looking at those tables. We spent lots of time in the previous chapter or so. Remember differentiating between the Z table, which is for really, really large samples, and then the T table, which is for samples that are less than 30. And then also remember about when we did this in the last chapter, we had to worry about whether the variance of the population was known or unknown. That's less important here. This is going to be the T distribution with n-2 degrees of freedom, and that's because there are 2 unknown parameters that have to be estimated. So there's a great picture of the normal distribution, and what we're trying to do is we're trying to formulate a test so that if in fact X does not predict Y, it'll fall inside of that light non-rejection region. But if we're going to reject, and notice there's a rejection region out to the right and a rejection region out to the left, which is a two-tailed test. You always do a two-tailed test in I shouldn't say that. Most of the time you do a two-tailed test when you're performing regression analysis. Now, the p-value is the smallest level of significance at which we can reject the null hypothesis. And so I want you to think about the alpha that we've talked about over the last couple of chapters. Alpha is some measure of our level of significance, like 1% or 5%. So if the p falls below, let's just pick 5%. If it falls below that, then we can reject the null hypothesis. All right, let's go take a look at an example here. We're trying to predict the price of a share of stock. So we get a slope coefficient is 0.6, standard error is 0.25, sample has 30 observations, so we're going to determine if the estimated slope coefficient of 0.6 is significantly different from 0. Now, what I want you to do is I want you to look just quickly at step 2. I want to give you kind of a big picture thing here. So look at that formula. We got 0.6 minus 0 over 0.25. So when is that number going to look an awful lot like 0? The 0.6 is the estimate, right? And 0.25 is the estimate of variability. What would force that number to look like 0 or be some number around 0? Well, the only way that it can be somewhere around 0 is if that denominator is a big number. I mean, suppose the standard error of this regression model were 25, not 0.25. Well, then that test statistic would be way smaller and it would be closer to 0. So really what we're doing here is we're looking at the relationship between the slope coefficient and its and some measure of risk, some measure of variability. Okay, if the variability is smaller, then we have a greater likelihood. All right, so let's work through the steps here. Step 1, state the hypothesis. That's that the null hypothesis is that beta 1 is equal to 0. Alternative is that it is not equal to 0. We can easily compute that test statistic from the results of the regression output that was on the previous page. Then we get out our t-value, so we look this number up. So we've got, we're going to do 95%, so we're going to put 2.5% in the left and 2.5% in the right tails. We look up 28 degrees of freedom, and we get a critical value of 2.048. So note the green line going down the middle of the normal distribution picture of the bell-shaped curve. That thing is going to be 0, so we put that all the way out there to 2.048. Our test statistic, it lies to the right of that. All right, so what do? We reject the null hypothesis, and we say that the slope coefficient is statistically significant. How about if we use the p-value approach? We're going to do the same couple of first steps. State the hypotheses, compute the test statistic, and then to kind of take a shortcut here, we're going to apply the central limit theorem, which says that, most distributions approach a normal distribution. And the t with 28, we're going to kind of do a little bit of rounding here, but that's not going to matter. And so we're looking for the probability that a z is going to be greater than 2.4. And we look up look up 2.4 on the z table. So remember, run your finger down to 2.0 and then run your finger over to 0.4, and you get the 99.18. And that's if you're looking at the entire z table. If you're only looking at half, then you're going to have to add 50.5 to the 4918. We get the 0082, multiply that by 2 because we're throwing it into both tails, and that's 1.64%. So our p-value is 1.64%, which is less than 5%. So we're going to reject the null hypothesis again. So we reject here using the critical value method. We reject it here using the p-value method. That brings us to this third method. Let's look at the confidence intervals. And remember that I talked about confidence intervals in the previous chapter, and what we're really thinking of is just a range. I always ask my children, I said this in the previous chapter, what grade do you think you made? What's the highest and what's the lowest? So a confidence interval just gives us a range. But unlike my children who took a German test last week, and I asked them what they made, and they both said, probably about a 90. And I said, what's the highest and lowest? And one said, the lowest I made was 85. The highest I made was 90. And the other one said, well, I might have made an 80, but I could have made a 95. So, this is just the way their 14-year-old brains kind of work. But here, with a confidence interval, with a regression analysis, we need to do this from a statistical perspective. So we need to use critical values from the table, and we need to use standard errors. So there's the point estimate, beta hat 1. Then we're going to add and subtract. So there we have the plus or minus. And all we're going to do is plus or minus the critical value times that standard error. So think about my children's estimate of a 90. They're going to do plus or minus. Now that's just working through their brains. But now they're going to look this up from a normal distribution, assuming they take thousands of German tests, and then the standard error of the outcomes of all of their thousands of German tests. Oh my gosh. Now you can hopefully see that from a statistical perspective, it's still a range. I still like that interpretation, but it's a statistical range with a level of confidence, in this case, 95%. So what we're going to say is that we have a 95% chance of generating beta 1 that's between these two numbers. That's the next step, by the way, for me to teach my children to do some confidence intervals. All right, so let's go back to our same example. There's the 95%. So beta hat sub 1, the slope coefficient is 0.6. We plus or minus 2.048. There's that critical value times the standard error of 0.25. And there's really no simple way to do this in your calculator. The way I would do it is I would put the 0.6 in the memory, and then I would do the plus or minus on the right side, and then I would do 2.048 times 0.25, and then I would multiply it by the memory, and then recall the memory, make it positive or negative, and so you get the 0.088 to 1.12. Oh, and by the way, let me read that last part down there. When testing the hypothesis using the confidence interval method, we reject the null if the interval does not contain 0. So it does not contain 0. So all three methods, the critical value, the p-value, and the confidence interval method provide us with the same results. And that takes us through this chapter 7. What we'll do next then is we'll go from one x variable, one independent variable, to multiple independent variables.